So my name is Ken Dockser. I'm a senior principal architect at Tenstorrent, and I'm going to talk to you today about the vector crypto extensions in the real world. So vector crypto has been ratified. Here's the link. It's part of the RISC-V GitHub. I usually find it, I just Google RISC-V crypto. So this specification was produced as part of the Cryptographic Extensions task group. We also did scalar crypto. The chair is Richard Newell, and I'm the vice chair and scribe for the specification. So, start off, what is cryptography? It is the art of keeping secrets secret. And there are three aspects, generally, of cryptography. One is confidentiality, another is integrity, and then the third is authenticity. So as you can see in the green here, our specification covers the first two. So confidentiality is what you think of normally when you're thinking of cryptography. It's your secret decoder ring. So it's hiding a message in plain sight. You encrypt a message, you can send it over the internet, you can put it on a billboard. Nobody can figure out what it is without the secure key. So we have two sets of extensions for different types of block ciphers for confidentiality. The first one is ZVKNED. I'm not going to read all of the names. You can read them. I'll just go to the what they are. So that's AES block cipher, and that's defined by NIST, used in the United States and other countries. And then we also support SM4 block ciphers, and that's part of the Chinese Shangmi standard. So for integrity, you want to make sure that the message that you received is the one that was sent. Some adversary didn't get in and cross out some of the words on your billboard or inject some noise on the signals being sent over the internet. So we use fingerprints of the message, unique fingerprints. And so we support SHA-2, which is a secure hash standard defined by NIST. There's SM3, which is also a secure hash standard, and that is part of Shangmi. And then we also have GCM, GMAC. These are not actually secure hashes. The last one is not a secure hash, but it is made secure by how it's used. And yeah, let me explain for a second what a secure hash is. A secure hash is a fingerprint of your message that is, let's say, so complex that somebody can't take your message, make a couple changes, and be able to figure out how to come up with the exact same fingerprint. It's just not feasible. For the GMAC, and I'm not going to go into it too much, one in theory could do it, but not in the way that it's actually done as part of the block cipher with GCM. So we have a few other extensions as part of the whole cryptographic extension. So ZVKT is similar to ZKT, and this is data independent execution latency. And the idea here is that an adversary can't tell what your data is by how long it takes an instruction to execute. So for example, people may be tempted to say, oh, for multiplication, if I'm going to multiply by 0, that's easy. I know the answer right away. It's 0. I'm not going to go through the whole pipeline. I'm going to give an answer right away. That could give an adversary some information, and they can potentially determine what your secure key is. You don't want that. So ZVKT lists several vector instructions, actually it's quite a long list, that have to be done. If you implement ZVKT, you have to execute these instructions with latency that is independent of the data values. And don't worry, divide is not included in there. You can still do early out for divide. ZVBC is, oh, I said I wasn't going to do that. Okay, we have vector carryless multiplication, also known as polynomial multiplication. This has a lot of uses. It can be used for elliptical curve cryptography. It can be used for GHASH calculation if you don't have the GHASH extension that I showed on the last slide. It can be used for CRC, which is a hash, but it's not a secure hash. And ZVBC, I don't know if you can kind of see, it's bold and it's kind of a dark green. So that is optional in the RISC-V application processor profile, RVA 23. It's optional because it is something that's very useful, especially as I was saying for CRC, but some people may not want to put it in the design just because of the size. ZVBB is vector basic bit manipulation. Oh, I did it again. I said the name of it. It's actually important that I did say the name of this extension because you'll notice it doesn't have a K in it, just like the last one. K stands for crypto, by the way. So we're very cryptic. So these two instructions are kind of general purpose. You can use them in cryptography, but they also fill gaps in the RISC-V vector offering. ZVBB actually is required in the RVA 23 profile draft specification. It's not finalized yet. ZVKB, okay. The vector cryptography bit manipulation instructions is a subset of the vector basic bit manipulation instructions. So it's the bit manip instructions that we initially put in that you need in order to implement the algorithms that I was talking about on the last page, AES, SHA-2, right? We also added instructions for SHA-3 in there. And yeah, to give you an example of what kind of instructions, there are things like rotate and not. Both of those are important for SHA-3. And then general bit manip instructions would be things like population count, find leading zeros. The next extensions in the specification are really collections of all of the previous extensions. So you have the NIST algorithm suite, and then that's AES, SHA-2, ZVKT, and ZVKB. So the cryptography, bit manip, and vector data independent execution. The next two extensions just add on additional features. So the next one includes carryless multiply, and the one after that includes GCM. We have the same kind of, here, maybe I can use the laser pointer. We have the same kind of extensions or packages for the Shangmi algorithms. So ZVKS includes SM3, SM4, and then also ZVKT and ZVKB. So you'll notice that these are kind of that dark green color. They are optional in RVA 23, and Mark talked about this a little bit this morning in the state of RISC-V. These are really, in a sense, mandatory options. The idea is that you choose one of these, you implement one of these, depending on your region.
Why is there not the CG?
You want the compressed instructions in there? Oh, the carryless. Okay, I thought you were making a joke. Okay. You can always, you can always mix and match. So we were saying, since the carryless multiply is usually used for implementing GCM, but if you already have the GHASH instruction, then you don't need the carryless multiply. But I think it'll be very common that people will do ZVKNG and ZVBC. Okay, so we designed these instructions looking at the algorithms themselves. And so in so doing, rather than copying others, we have a lot of advantages in the performance of these instructions. And when I say performance, I mean higher throughput and lower latency. So for the block ciphers, we have a single instruction per round. So if you're doing AES 128 encryption, there are 11 rounds. Most people think there are 10 rounds, but there's a 0th round, so there really are 11 rounds. So we have instructions. Each time you execute one of these instructions, it performs 1 round for the encryption. Not all architectures do that. Also, we have special instructions for the first round, which you might call the 0th round, all of the middle rounds, which is the bulk of it, and then the final round, because there are differences between them. And that helps reduce code size. And then I mentioned the different rounds. You use a different round key for each round within a block, and we have a single instruction that produces the next round key. For keyed hash, so this is the GHASH instruction, we have a single instruction that performs the whole round, I call it a round of GHASH algorithm. So I'm not aware of any other architecture, certainly none of the leading architectures have this feature. So they perform GHASH through a series of carrierless multiplies and exclusive ORs. So just having this instruction saves you maybe 10, 15 instructions. So it's a really nice one to have. Oh, so I said, yeah, we looked at the algorithms to determine how to come up with these instructions, but we also implement them. So we want to make sure that they're implementable. So these instructions, it depends on your implementation, your technology frequency, but the idea is you can implement them in 3 or 4 cycles of latency. And then for the secure hash, for SHA-512 in SM3, we update 256 bits of state per instruction. The competitors at best do 128 bits. They're not competitors, they're just other leading architectures. And then we have independent compression instructions for SHA-2, which saves you a permute or a slide instruction. So it allows you to have lower latency. So how do you write high performance cryptographic code? I'm gonna leave you in suspense there for a second. Of course, you can read the answer. So for, so you want to exploit parallelism that's available in the implementation that you're targeting. So you really, the code has to be tailored somehow to the target implementation. So if the processor that you're going to be running on has a 256-bit wide vector data path, or really this is the register length, VLEN equals 256, that means you can do 228-bit instructions in parallel. So you could do 2 AES encryptions in parallel. So you want the best performance, use the full width of the data path. Also, many implementations have multiple vector pipes. So you want to be able to use all of the pipes in parallel. So you can use the full width of the data path and then all of the pipes, and you use all of the pipes by interleaving independent instructions. You don't want to just do your first round instruction, wait 3 cycles to get the result, and then do your second round instruction and wait 3 cycles. If you interleave instructions from different rounds, you can get much higher throughput. So you're using those bubbles to do useful things. And then, yeah, it also hides your latency. So it really doesn't make that much difference if your latency is 3 cycles or 4 cycles for an instruction, because you're doing more in parallel. And then you want to create parallelism where you can. And so you can do that by breaking dependencies. I'll talk about that in the next slide. And then if all else fails, handle multiple buffers at a time. So, and I'll talk about that a little bit more in this last slide. Okay, so the cryptographic algorithms have some innate parallelism in them. So encryption or decryption of a single block, all the rounds that I was talking about, that's inherently sequential, but there are different modes of operation, how you're dealing with multiple blocks. And in some cases, some modes are sequential. Cipher block chaining encryption, but not decryption, is inherently sequential. But plenty of the other modes are parallelizable. Electronic code book, counter mode, or Galois counter mode. And so those you can get much higher performance, as I was talking about, interleaving the instructions. The keyed hash instruction, if you look at the algorithm for GHASH, at first glance, it's serialized. You have to complete each hash before you can go on to the next. But you can use this thing we like to call math and break that dependency. And you can create these hash subkeys. We don't need to get into too much of the details. But basically, you can accumulate partial hashes in parallel and then combine them all at the end and get the same hash as if you had done it in serial. And then for the secure hashes, SHA-2, SM3, they're inherently sequential. So this is what I was talking about. Do multiple buffers in parallel. If you're going to be sending multiple messages, you can create multiple signatures by working on those different messages in parallel. Or another application, not that it's security related, but since these signatures, the hashes, are unique, you can hash all of your files on a hard disk, for example. If the hashes match, the files are the same. So you can go through your hard disk and create hashes for all of the files in parallel, and then find where you have redundancies. So, are there any questions? Yes?
Do you have any refreshing to support like the asymmetric function, like the RISC-V?
No, not currently. Maybe, Rich. Yeah, we're not currently supporting any sort of asymmetric that may come under the post-quantum. So yeah, the question is about some of the. Right. So yeah, so the question is about asymmetric cryptographic hashes, if we're, I'm sorry, not cryptographic operations. There isn't a plan to support them right now. The RISC-V Vector architecture does have instructions that allow you to do like arbitrary precision arithmetic, so it can help speed it up. But really, we're concentrating on post-quantum cryptography, and that will provide what you need. Any other questions? Oh, you're asking if we have random number generation support. So actually in the scalar cryptography extension, we do have an interface. It's a CSR that will access an entropy source and tell you how much entropy you're getting. Any other questions? Okay. You can always reach me. You can send me email, stop me in the hall, whatever. Thank you very much.